When I was first asked to speak here, actually, I was given about 20 minutes to do, the science of conservation cleaning, textile cleaning. It was actually a pretty daunting task. I really wanted to actually rather just take the time that I was given to actually introduce you to something that we've been looking into in terms of cleaning on textiles in general, but I think it has an application in terms of tapestries as well. If we step back from textile conservation, if we step back from this conference in general and just think about, for instance, other fields, the idea of microemulsions. Microemulsions has essentially been a buzzword for about 25, 30 years, for instance, in other endeavors. Microemulsions are, like the name suggests, essentially very small distributions of solvent and water put together in one form or another. But it's interesting, the mantra in other fields has been for a number of years now, essentially lean, mean, and green. And there's no reason to think that there isn't a kind of equivalent in conservation and a use for these kinds of materials as well. Microemulsions essentially are, as I say, small distributions of solvent and water put together, for instance. They've found a lot of impact in other fields because they essentially solve a lot of solvation problems. Because they're broad spectrum, because they embrace the chemistry of both solvents and water simultaneously, they can actually bring a lot of materials into solution, disperse a lot of materials that otherwise were very problematic, for instance. It seems to me that there's also a kind of application in terms of tapestry or textile cleaning where we need that same kind of lean, mean, and green. In other words, we need a very specific sort of cleaning system. We need something that we can apply even locally if we have to, for instance. And at the same time have something that, for instance, is broad spectrum. It's kind of a dichotomy. But we also worry about toxicity of materials, the things that we're going to handle in the normal studio sort of context. The fact is, out of this conference, it's been an eye-opening thing for me, for instance, because again, there seems to be a kind of need for both simultaneously overall treatments of these kinds of structures, but also specific treatments, specific areas. There's no reason to think that, for instance, soiling is even overall across the surface of a tapestry. Of course, certain soils will be accumulated in certain areas over others, for instance. Things have been treated differentially in the past, for instance. And we may want to rethink this idea and develop tools in both directions. In other words, look at overall treatments and what we can do, but also look at what we can do in a practical scale in the studio in terms of local sorts of treatments. Can I buy back the aesthetic that I want in this kind of object by working locally rather than overall? Tina actually made a wonderful analogy, at least to me, on Sunday when she compared, for instance, the restoration of tapestries to painting conservation. The idea of actually completing images, filling out narratives, for instance, was very much analogous to painting conservation. And here I'd actually take that a step further and say that the representation of a surface through cleaning, for instance, has both, a preservative sort of act. In other words, we are saving some wear and tear, I think, on those structures. But it also has an aesthetic impact that cleaning in some areas, may be required a little bit more than others. When we clean a painting, for instance, we may hold back on the lights and actually clean a little bit more in darker areas to achieve a kind of aesthetic balance within an image. And I think you actually may want to think about those kinds of approaches as well. It's really seductive. The other thing that I've come away from this conference thinking about is this idea, again, of dry cleaning and wet cleaning. It's absolutely seductive to want to do wet cleaning of these kinds of objects because we know in our hearts that we can remove acidic material, degradation products, salts, things that we know will further deteriorate those kinds of structures. But at the same time, it's a risk to the object itself because we worry about dye movement, bleeding, transfer, things like that, for instance, within the structures. And of course, the overall impact on the structures themselves mechanically, the weight of those kinds of operations, the stresses that are developed in those kinds of wet cleaning things. In counterpoint to that, dry cleaning, for instance, is also seductive because it circumvents the problem of water. If I can generally bring a broad solvent system to these kinds of structures, something that won't move the dyes, won't move anything else, will just simply be a carrier for a small water phase, like we do in dry cleaning, for instance, then we can control some of those problems with water and at the same time deliver water in a form that we may actually have a little bit of control over. I mean, what I saw this morning, for instance, in a lot of the talks was, again, this drive of finding ways of controlling the application of water, doing as much as you can with water. In other words, controlling how it's applied and how it's removed from these kinds of structures, adding adjuvant materials like surfactants to extend what water can do itself. But at some point, we may want to also think about dry cleaning or dry cleaning models. In other words, it may be so much more efficient to come at these problems with a dry cleaning sort of model than the wet cleaning sort of model, just for the problems that are inherent in sort of wet cleaning. Well, the downside of that is obvious, of course, because how can we dry clean these huge structures? It's not a very practical thing. There really aren't dry cleaning plants that can accept these huge textiles, and I don't think I'd want to put a tapestry in one of those systems anyway, necessarily. And yet we do have this need to bring solvent and water simultaneously, I think, to these structures. Well, what can we do on a studio scale? What can we do on a smaller scale, maybe even locally within these structures? Are there ways to, for instance, be a little more green? Are there solvents that we can handle safely in the studio that can make these kinds of water and solvent combinations that we know are a little more efficient? We do have to worry about the stability of emulsions, though. I'm going to introduce a new idea today, I think, to you all, which is this idea of microemulsions. A microemulsion really is, as I say, a mixture of solvent and water put together in a stable form, but it's in a very unusual sort of way. It's not like what you think of with a normal emulsion. In a standard dry cleaning mixture, it might be 95% solvent, a lot of surfactant, very strong surfactants, high HLB surfactants, and a little bit of water. But those kinds of traditional emulsions, macroemulsions we'll call them, basically take a lot of energy. They take a lot of surfactant, and they take a lot of energy, for instance, to make sure that they're stable, that they can disperse water in those systems. That's why the mechanics are needed essentially during the dry cleaning process, the tumbling, the rolling, the movement of fabrics and things that are cleaned that way. The stability is so great, actually, that it might be better to think about stabilizing emulsions in another way. And that's essentially what the heart of these microemulsion sort of preparations are. They're thermodynamically stable, and they require really virtually no energy to stabilize them as forms. I am going to touch on toxicity of solvents and dry cleaning methods because obviously I want to propose at least, or to think about, for instance, all the panoply of solvents that are available to us now. We think of dry cleaning as involving, for instance, perchloroethylene or mineral spirits or those kinds of things, but in other fields, in allied fields that have used and made these kinds of emulsions, there has been the introduction over the last 25 or 30 years just a wide range of solvents that are very non-polar things, non-water miscible solvents that are equally effective and not toxic materials, for instance. And I'm going to show you one today. We do have to worry about disposal of these things. Well, again, we want green materials, but again, even that's a subject in its own right. What does the word green mean? I'm going to show you two materials, a surfactant and a solvent, that can be broken down in a very specific way to very non-toxic sorts of materials. And the last thing is, again, I want to come back to this idea of essentially doing things by hand, because we won't always necessarily have a studio space or access to or a need for necessarily mechanized systems. There are things that we may want to do on a hand scale, for instance, and we'll want to be able to make these things ourselves. We want them to go together in a very easy sort of way if we can. Microemulsions are liquid dispersions of water and oil that are made homogeneous, transparent or translucent, and thermodynamically stable by the addition of relatively large amounts of surfactant and co-surfactant having diameters of the droplets in the range of 100 to 1,000 angstroms, 10 to 100 nanometers. This isn't a new idea, these kinds of very fine dispersions, and that really is the difference is. You'll see that the size of these dispersions of water and solvent or solvent and water are on a very fine scale. So fine, in fact, that these kinds of preparations don't look milky like traditional emulsions. These are going to be transparent sort of materials because the size of phase distribution is so small below the wavelength of light that these look like transparent materials. The term microemulsion is a fairly new term. It was actually introduced in the late 1950s basically to describe a multi-phase system consisting of water, oil, surfactant, and alcohol, which forms those kinds of transparent solutions. But it's not a new idea. Australian housewives essentially, for instance, in the 19th century, We're using combinations of water, eucalyptus oil, soap flakes, white spirit mixtures to wash wool, for instance. And those, in essence, even at that early point, were really what we now know as microemulsion type systems. The waxes that were used by, soluble waxes, the liquid waxes that were used by Rodenwald in 1928, for instance, again are an example of the very early use of these things. It isn't a new idea, but the newness of all of these things really has come in the last 25, 30 years in understanding exactly how these microemulsions or microdispersions form, why they're stable, and where they can be applied, for instance. It's really in the 1970s and 80s when it's been recognized that these systems could improve all sorts of things. Now, if we go outside of conservation, there's virtually no technological field that hasn't made use of these kinds of microemulsion arrangements. I'm going to actually draw from pharmaceutical and cosmetic chemistry fields because essentially they've done a lot of the legwork for us. They've actually begun looking at a lot of materials, have worked out the logistics of making some of these things, and even have brought in new solvents to make these things, virtually because of the toxicity effects of some of these materials. In fact, the system that I'm going to show you, just as an example today, is really drawn from pharmaceutical chemistry and more than anything else, for instance. It is a non-toxic system. As I say, the particle size of these kinds of microemulsions, where we have one phase dispersed in another, is very, very small. When the particle size of a dispersed phase is about 100 nanometers or less, for instance, we don't see that micelle. We don't see that distributed phase. It looks like a clear solution. These are really transparent materials in appearance, and you'll see a couple of them in a moment. But they're thermodynamically stable. In other words, we don't have to do a lot of shaking. We don't have to move these kinds of systems around or input a lot of mechanical energy to both form the micelles and to open them up, to include soils, to have them close again. In other words, to make them efficient cleaning systems, there's really virtually no mechanical energy or energy in that way that needs to be inputted into these systems. They're optically clear. Their surface area is very high, for instance, in these kinds of preparations, and they have very high solubilizing capacities. A typical microemulsion, again, as I say, might be on the order of a micelle that might be on the order of 10 to 100, 10 to 200 nanometers. But again, below the wavelength, essentially, of light. So these kinds of preparations are going to be transparent when we make these kinds of arrangements. A traditional emulsion is going to be much bigger, and it's going to be big enough to scatter light. So we'll see right away the difference between those things optically. But a bigger difference, essentially, is in the construction and the use of surfactants to make these kinds of micelles, to make these arrangements. In a traditional emulsion, for instance, we might actually use a surfactant like lauryl sulfate. We might use something like that at a high enough concentration to stabilize the boundary between a hydrophobic phase, an oil and water, or if we're making the reverse like a dry cleaning mixture, water in solvent, water and oil type arrangements, for instance. But in any event, we actually use a lot of surfactant. And in a traditional emulsion, those kinds of surfactants can get down to a certain size, but they're very stiff sort of things. They stabilize the boundary between these two very different materials, but we have to work mechanically to open up that boundary, to get between those surfactants, to allow soils or materials to be included in one phase, for instance, the dispersed phase. In a microemulsion, not only are they smaller in size, but they always include surfactants of a very peculiar sort of structure. They always include surfactants that are very flexible in size, so that we can actually geometrically have very much smaller micelles. But they also include what's called a co-solvent, a material that gives them added flexibility. The co-solvent makes them and allows us to make very small dispersed phases of these materials and still stabilize the boundary between, let's say, hydrophobic and hydrophilic material. And the other thing that it does is by adding a solvent, a co-solvent to these kinds of systems, they actually very much lower the surface tension even further. It's so much easier to open these structures up, include soils in them, and close them back again. They want to thermodynamically be very close to one another. We've brought these separate phases very close in terms of surface energy with these kinds of arrangements. Again, just a quick comparison of different systems. Emulsions consist roughly of spherical droplets of one phase and another. In microemulsions, they constantly evolve between various structures ranging from droplet-like swollen micelles to what's called a bicontinuous material. Droplet size is much bigger in traditional emulsions. In microemulsions, they're much smaller. Like I say, they're so small that we can't really see them. They're very transparent sort of preparations. Most emulsions are opaque. Microemulsions are transparent. The interfacial tension in a normal, traditional macro emulsion is essentially on the order of 20 to 50 millinewtons per meter. The interfacial tension can be reduced much, much lower than that in these microemulsions, down to about 4 to 10, for instance. Ordinary emulsions, while we may make ordinary emulsions with surfactants of a sufficient HLB to stabilize oil and water or water and oil type emulsions, they still are driven by the fact that eventually they will settle out. Gravity will pull them together. When they're absorbed onto surfaces, we break that stabilized system. Traditional emulsions, really, we have to work very hard, in other words, to keep them in that emulsified sort of form. With a microemulsion, they are thermodynamically stable, and we're not going to have to go through any of that. We don't need any kind of movement in solution, mechanical action that way. These are lyophobic. These are on the border between lyophobic and lyophilic colloids. These require intense agitation for their formation and their use, essentially. These generally are obtained by gentle mixing of ingredients together and can be used simply like we might use a solution. Put it on something, draw it through that, rinse it away, for instance. The important conditions, though, surfactants must be carefully chosen that an ultra-low interfacial tension must be achieved with these kinds of things. They can be attained at the water and oil interfaces, which is a prime requirement for these kinds of microemulsions. In other words, there are only going to be certain surfactants that will allow us to do this kind of thing. And it's really the combination of surfactant and solvent that allows us to get to those very, very low surface tensions. The concentration of the surfactant must be high enough to provide the number of surfactant molecules to stabilize these microdroplets. The interface must be flexible or fluid enough to promote the formation of microemulsions. Again, what makes these different from standard macroemulsions is that really we're probably looking at surfactants that are blended with solvents to make them smaller, make them flexible, make them easier to include materials within those separate phases. That's essentially the heart of a microemulsion system. Surfactant and alcohol mixtures possess a variety of exceptional properties. I mean, a lot of times the combination of surfactant and alcohol, when it's at the right proportion and we have the right surfactant structure, will create these microemulsions spontaneously. In the past, some of these preparations that included surfactant and alcohol at very high concentrations, for instance, in cleaning systems, might very well have been microemulsion sort of containing systems. It's not unusual to see a stoichiometry of about 2 to 1, that is, 2 molecules of surfactant to alcohol in these kinds of preparations, and we'll kind of use that as a design tool. The synergism between alcohol results in a less power demand for emulsification. This effect, called spontaneous emulsification, and its mechanism is still a matter of controversial discussion. But essentially, it's that combination, as I say, of surfactant and solvent, surfactant and alcohol usually, that basically will allow us to create these stable arrangements. On oil and water, it can be either oil and water or water and oil in those traditional designations. If we have a solvent dispersed in a large amount of water, where water is the continuous phase, we can form microemulsions, again, emulsions on a very fine scale. We can do the opposite, of course, with the same sort of surfactant system by turning it around. In water and oil type emulsions, which are more like traditional dry cleaning methods, we can actually take a little bit of water and disperse it in a continuous phase of solvent. And it's this water and oil kind of microemulsion that I'm going to suggest will be very interesting for us, for spot cleaning, for that dry cleaning, for that kind of application. Traditionally, there have been 3 types, as I say, oil and water, water and oil, and what's been called the bicontinuous sort of microemulsion. All of these things essentially represent a continuum from macroscopic emulsion to microscopic to inversion point sort of arrangements where it's not clear which is the continuous and which is the dispersed phase. To, if just by adding a little bit of excess of solvent or water one way or the other, we can push this kind of equilibrium one way or the other. We can go out and buy these kinds of inverse materials. In fact, Dow makes a product called Inverse 1000, 2000, 4000. They're actually pre-made mixtures of alcohol and water that we can dilute with water, or we can dilute with solvent, for instance, to produce the microemulsion of our choice. The advantage is that they're thermodynamically stable. The disadvantage, of course, may be in the fact that we really actually are now using much higher concentrations of surfactant and solvent than we might be used to. But the fact is, in this kind of water and oil type dispersion or microemulsion I'm going to show you in a moment, we can actually, the surfactant system is very soluble in the solvent, and we can actually easily rinse it away. Microemulsion stability is influenced by a number of things in solution, but including pH and temperature. Traditionally, those materials have been given designations. You might have heard these things: Windsor 1, Windsor 2, Windsor 3. It's really this Windsor 2 type arrangement that, again, we're going to concentrate on just for the remaining moments that I have. Type 2 is really a water and oil microemulsion, where we have really a large phase of solvent. Solvent there not to swell fibers like wool and silk, but a small phase of water to affect the cleaning in this case, for instance. Clearance in this case is easy because a microemulsion, we can simply take a water and oil type emulsion, something with a small amount of water and a large volume of solvent, and dilute it further with solvent and simply remove that small water phase. That's the point of these kinds of arrangements. Small amounts of water in a dispersed form, in a microemulsion, is a way of controlling the chemistry of water. As long as it's in that emulsion form, we're not going to lose it to the fiber. We're not going to wet that fiber in a way that we might with an outright aqueous solution. And we can dilute it, move it out, disperse it, and acquire the soils that we want in these microemulsion phases of water, and then move them out with a solvent rinse, for instance. I'm going to give you an example of one really quickly. This is one, essentially, that we've used as a model system. In this system, really, I'm going to show you actually two versions of it, and they're only going to vary in terms of the proportion of materials. But a system in this case, the surfactant could be something like Bridge 97 with a small amount of an alcohol mixed with it in maybe that 2-to-1 ratio. Bridge 97 is a palmitic acid derivative. It's actually an ethoxylated version of palmitic acid. So when it breaks down, essentially what it forms or leaves behind is just simply a soap like palmitic acid. The solvent in this case is a non-solvent. The solvent is a non-water miscible solvent, of course, to form the emulsion. This will be the continuous phase in one of these emulsions. It's a relatively new solvent that you won't be used to. It's called isopropyl palmitate. And again, it's nothing more than palmitic acid as an isopropyl ester. That, again, is a solvent that isn't miscible with water, but non-toxic. It can simply be split by hydrolysis back to isopropanol and palmitic acid. It's a green-type solvent, for instance, being used in pharmaceutical and cosmetic sort of chemistry. And then, of course, there is going to be a small amount of water phase. Now, if we make one of these emulsions, let's say we make the oil and water type form, surfactant at this proportion, solvent at this proportion, and water at this proportion, basically we have a pH in this range in these materials by themselves, a fairly low conductivity, in other words, an isotonic sort of condition, essentially to what a textile might be, and the viscosity is very low. This material will take water, distribute it in the water, bring that distributed phase or microemulsion of water into a structure, but we're not fighting the wetting of water into that textile. Because of the very low surface tension of the isopropyl palmitate, we're essentially wetting very deeply into those fiber structures, bringing that dispersed phase of water as a small, more penetrating sort of phase of material, and then eventually bringing it out with the dirt acquired within it. This is a phase diagram, but the phase diagram essentially is constructed to give us a kind of roadmap of construction of these materials. This is the phase diagram for that Bridge 97 isopropyl palmitate and water sort of tri-system. Here, the proportion of solvent gets bigger along this axis as we move to the right. The amount of surfactant and alcohol proportion is increased as we go up this scale on this side, and the amount of water goes up this side. It's in this blue area here that we can actually form these stable microemulsions. So we actually have the latitude to design anywhere within this triangle to create these materials. Now, if we take the exact proportions of, for instance, about 15 parts of water, whatever this was, 1, 2, 3, 4 parts, 40 parts of the solvent, and about 45 parts of the surfactant. In other words, if we create a mixture of those three components at this point, we have one of those stable sort of microemulsions that's a water and oil type, which is the dry cleaning type, in other words, that I'm talking about. It's very easy to do. Here's the surfactant and solvent mixture. It doesn't have to be butanol. There are other alcohols that can be substituted in here. But it's a clear solution. The solvent is a clear solution. The water, with whatever else that we need in that water, can be all three put together to form essentially this microemulsion. It doesn't look like a two-phase system, but essentially it is a two-phase system where it's mostly solvent with a tiny, tiny bit of water. Increased penetration, increased ability to pick up soiling material, and the ability to be rinsed away essentially in the same solvent if we need to. I'm going to just finish up with the last two slides here. Essentially, they're brought together, and by simple mixing, these things make the emulsion. We don't have to shake. We don't have to do anything elaborate to pull them together, for instance. They're thermodynamically stable. Just wanted to show you one last bit of a fragment of a tapestry here. Again, we use a model sort of soiling mixture, and if you're interested in that, I can tell you a little bit more about that after the conference. But we essentially will soil this material with a known material and then go ahead and clean it with the microemulsion. In this particular area that I've outlined with the red line, this is actually an area that was cleaned essentially with the microemulsion. This was after wet cleaning. This was after solvent cleaning. This was the additional material, for instance, that was pulled out onto, in this case, a simple blotter, clean blotter. Anyway, I'd like to thank the Metropolitan Museum, both the Conservation Department here and at the Cloisters. I'd like to thank Sarah and Nicole for all of their hard work. Thank you for bearing with me this afternoon.